living in. Let me tell ya. Yeah, it's a world that man can...
Here we have a little bit more complicated circuit. It has, for example, two batteries, so we cannot solve this just by calculating the equivalent resistance and lumping them all together. So we have to resort to Kirchoff's laws. And to prepare for that, let's note the currents that we want to solve in this problem. So here's battery 1, E1. So let's make I1 go that direction. It's just a guess, because the positive voltage is here, so it will likely drive current going this way. And then here we have E2, the positive terminal is here, so that's probably... Okay, so let's call this one in fact I3, because there's a resistor 3 there. So here we have I3, and it just leaves the positive terminal. That's the thinking here. And here we have I1, I3. They both combine in this junction, and they have nowhere else to go except this direction. So we call this one I2. So in fact, I already used the first Kirchoff's law here, saying that in a junction point, the sum of incoming currents I1 plus I2, I3 must equal I1. So that's one equation for our system. We need at least two more, because we have three unknowns, I1, I2, and I3. Next, we will use the Kirchoff's second rule that says that the change in potential around any closed loop should total to zero. So let's study the upper loops, and we go in this direction, clockwise direction around this loop. So we're starting from this point, and this battery raises the voltage by E1. So we got E1. Then, because we are going with the current over the R1, so the potential or the voltage drops by amount I1 times R1. So we are here. And then we come here, we now have I2 instead of I1. So I2 goes over this resistor, and because we're moving in the same direction as the supposed current, this will drop the voltage, so we get minus I2 times R2. And let's use this piece of information. So we replace I2 by this relationship, so we can get rid of the I2. After all, we're trying to eliminate variables as we go along, so rewriting this E1 minus I1 R1 minus I2 is now I1 plus I3 times R2. So this must be 0. So far we have two equations, so we need one more. In fact, we have two choices. We could evaluate this loop, or then we could do the big loop. It doesn't really matter. One of them is easier than the other, and I try them both. And the fact is that we want to analyze this big loop going all the way around the perimeter. So let's start from this point again. In this case, we first build up potential E2, because we go from minus to positive over the battery. Then we have I3 flowing through R3, and because it's the same direction as we are going around the loop, the potential will drop there. So we have I3 minus I3 times R3. Now we get here, and now we just have to go this way. And now over here we are going against the current, so that will raise the potential by I1 times R1, because current is going this way and in our loop we are going this way. And now we are here, and now we just need to cross this battery. We're going to high to low, so we are dropping the voltage by E1. And this, according to Kirchoff, must equal to 0, because we started from this point and came back. Hence we have our 3 equations and 3 unknowns, so it can't be solved. But in fact we already eliminated the I2, so in fact we have these 2 equations, which include 2 unknowns, I3 and I1. So first step, let's solve what is I1 just from this. So I1 will be E1 goes to the other side, so does E2, E1 minus E2, and then this whole chunk goes over there, so that's going to be plus I3 R3, and we divide the whole thing by R1. And now that we know I1, we could in fact plug it into this one. So, but let's rearrange this one first. So combine the terms. So we get E1, then we have minus I1 R1, and then we have this term R2, and we are left with negative I3 minus R2 equals 0. And now we're ready to plug in this I1 into here. So let's do it over here. So we got E1 minus this whole thing, E1 minus E2 plus I3 R3 divided by R1, then this term R1 plus R2, and finally minus I3 R2, this equals 0. So let's multiply both sides by R1 so we get rid of this denominator. Hence we get E1 R1 minus E1 minus E2 plus I3 R3 R1 plus R2 minus I3 R2. This equals 0. Now let's collect the terms that have I3 in them so we can solve for I3 eventually. So we get I3, first of all, negative I3 R, this is R3, so negative I1 R3, negative I1, so we get R3 from here, and it's multiplying this term as well, so R1 plus R2, what else, and then we have negative I3 times R2, so plus R2, and then the rest. Here we have plus E1 R1, and then these guys are multiplying that, so negative E1 minus E2 times R1 plus R2. This equals 0. Now we can solve for I1. So I bring this to the other side and divide by the whole thing. So I get, let's do it this way to be clear, E1 R1 minus E1 minus E2 R1 plus R2. That's it. Divided by this thing, R3 R1 plus R2 plus R2. This whole thing equals I1. And now we can simplify this a little bit. So E1 R1, there's also a negative version of that, minus E1 R1. So this guy will cancel with that pair, and for E1 that leaves only minus E1 times R2, minus E1 R2. And then the other one, E2, is just negative negative, that's positive, plus E2 R1 plus R2. And that divided by this guy. Alright, I made a little mistake when I was multiplying everything by R1, so I forgot to multiply this one, so this one must also have the R1. Now we have 0, which means here's also R1, and here we have R1. Okay, so we have R1, R2 plus, multiplying that open, R1, R3, R1 times R3, and then finally R2 times R3. I'm running out of space here, but if we plug in all these values for the resistors and these voltages, we will get 0.148 amperes for I1. And because this is positive, the direction of current is indeed to the right here. And now we could go on, and once we solve the I1, we could solve from this equation for I3. And once we know I3, we could plug it in here and get the I2, so work backwards. I'm not going to do that explicitly because that's not the lesson to be learned from here. The key thing to take home is that we know how to use the Kirchoff's laws. The current sum at a junction, so whatever comes in must come out. Charge is conserved, and when you go around the circuit in loops, the energy doesn't disappear anywhere. Energy is conserved, which means electric potential is conserved, so hence we get over a full loop 0 as the total change in potential, electric potential, which means also in potential energy. And as you can see, these systems of equations, they get pretty laborious to solve if we have anything more complicated. There is no way around it, and usually these kind of equations or circuits are solved using computer softwares that will do the tedious work much quicker than a human could.